Hello there and welcome to Science with Sleepy. I'm so glad you found your way here. Maybe you had a long day, or maybe you're the kind of person who likes falling asleep to deep thoughts about the vast distances between galaxies. Either way, tonight's journey is for you. You've got nothing to do but rest. Let your mind relax, your breathing slow, and your body grow light as if gravity itself has softened. Because tonight we aren't simply thinking about space travel. We're drifting through the deepest questions about our future among the stars. We're asking when humanity might travel between galaxies, not just to nearby stars, not just across our own galaxy, but between galaxies themselves, to Andromeda, to the Triangulum Galaxy, to galaxies so far away that light takes millions of years to reach us. Picture this: you're looking up at the night sky, you see stars. Bright points of light scattered across the darkness. But those stars are all in our galaxy, the Milky Way, one galaxy among trillions. What if you could look up and see entire galaxies? What if you could travel to them? What if humanity could become an intergalactic species? This question touches on something profound. It's about our place in the universe. It's about what might be possible. It's about the future of humanity itself. And beneath this question lies something deeper, the science that makes it seem impossible, the theoretical solutions that might make it possible, and the timelines that might tell us when. We'll travel gently from the scale of intergalactic space to the physics barriers we face. From current space travel capabilities to theoretical solutions like wormholes and warp drives. From the energy problems to the biological challenges. From optimistic timelines to realistic ones, all in calm language that is easy to follow. Some of what you hear tonight may surprise you. Some of it may spark curiosity as you drift off to sleep. And just before we begin, if these calm, curious explorations help you unwind or give you a quiet way to end your day, consider liking and subscribing to the channel. It helps others find their way here too. One sleepy soul at a time. Now let's begin. Right now, as you rest, galaxies are moving through space, billions of them. Each containing billions of stars, each separated by vast distances. The nearest galaxy to our own is called Andromeda. It's 2.5 million light-years away. That means light, traveling at 282 miles per second, takes 2.5 million years to reach us from there. With our current technology, reaching Andromeda would take about 50 billion years. That's longer than the universe has existed, longer than Earth has existed. Longer than life itself has existed. So the question becomes, when might intergalactic space travel become possible, and what would it take to make it happen? Chapter 1: The Scale of Intergalactic Space. To understand when intergalactic space travel might become possible, we first need to understand what we're talking about. What does intergalactic actually mean, and how vast are the distances we're considering? Let's start with something familiar: our solar system. Earth orbits the Sun at a distance of about 93 million miles. That's one astronomical unit. It takes light about 8 minutes to travel from the Sun to Earth. That's fast. Really fast. Light can circle Earth 7 times in 1 second, but even at that speed, light takes time to travel. Now let's think bigger. Our galaxy, the Milky Way. It's a spiral galaxy, shaped like a spinning pinwheel. It contains between 100 and 400 billion stars. Recent measurements from the European Space Agency's Gaia mission suggest the number might be closer to 200 billion stars. Each of these stars could have planets. Each could be a solar system like our own. The Milky Way is enormous. It's about 100,000 light-years across. That means if you could travel at the speed of light, it would take you 100,000 years to cross from one side to the other. But here's the thing. We can't travel at the speed of light, not even close. Our fastest spacecraft travel at about 430,000 miles per hour. That's the Parker Solar Probe, the fastest thing humans have ever built. But even at that speed, crossing the Milky Way would take millions of years. Recent measurements from the Gaia Space Observatory, launched in 2013, have refined our understanding of the Milky Way's structure. The galaxy's disk is actually about 1,000 light-years thick at the center, but only about 300 light-years thick at the edges. The central bulge, where most of the older stars reside, extends about 10,000 light-years from the galactic center. The Milky Way's total mass is estimated at about 1.5 trillion solar masses, with most of that mass being dark matter, mysterious matter, that we can't see but whose gravitational effects we can measure. The Milky Way rotates, completing one full rotation about every 225 to 250 million years. This means that since the Sun formed 4.6 billion years ago, it has completed about 18 to 20 galactic rotations. The Sun orbits the galactic center at about 515,000 miles per hour, but relative to nearby stars, we're moving at about 43,000 miles per hour. These measurements come from decades of observations, and have been dramatically improved by the Gaia mission, which has mapped the positions and motions of over 1.8 billion stars. But wait, we're not talking about traveling within our galaxy, we're talking about traveling between galaxies. That's different, that's much farther. The nearest galaxy to the Milky Way is called the Andromeda galaxy. It's also called Messier 31, or M31 for short. It's visible from Earth on a clear night. If you know where to look, you can see it with the naked eye. It looks like a faint smudge of light. But that smudge is actually an entire galaxy, about the same size as the Milky Way, containing hundreds of billions of stars. Andromeda is 2.5 million light-years away. Let's think about what that means. A light-year is the distance light travels in 1 year. Light moves at 186,282 miles per second, or 299,792,458 meters per second in the metric system. In 1 year, light travels about 5.88 trillion miles, or 9.46 trillion kilometers. That's 5.88 followed by 12 zeros. It's a number so large it's hard to imagine. So 2.5 million light-years means light travels for 2.5 million years to get from Andromeda to us. The light we see from Andromeda tonight left that galaxy 2.5 million years ago. When that light began its journey, early humans were just beginning to walk upright. Mammoths still roamed the Earth. The continents were in different positions. That's how far away Andromeda is. The distance to Andromeda was first accurately measured by astronomer Edwin Hubble in 1923. He used Cepheid variable stars, stars whose brightness varies in a predictable pattern, as cosmic distance markers. By observing how bright these stars appeared in Andromeda compared to similar stars in our own galaxy, Hubble could calculate the distance. His measurement of 900,000 light-years was later refined, and today we know Andromeda is 2.537 million light-years away, with an uncertainty of only about 0.1 million light-years. This precision comes from decades of observations, using increasingly sophisticated telescopes and techniques. Andromeda is actually larger than the Milky Way. It spans about 220,000 light-years across, compared to the Milky Way's 100,000 light-years. It contains an estimated 1 trillion stars, compared to our galaxy's 200 billion. Andromeda's mass is about 1.2 trillion solar masses, slightly less than the Milky Way's 1.5 trillion, but still enormous. Recent observations from the Hubble Space Telescope have revealed that Andromeda has a double nucleus, two bright spots at its center, possibly the remnants of a smaller galaxy that Andromeda absorbed billions of years ago. If we wanted to travel to Andromeda using current technology, it would take about 50 billion years. That's 50 billion years. The universe itself is only about 13.8 billion years old. So reaching Andromeda with current technology would take almost 4 times longer than the universe has existed. It's not just difficult, it seems impossible. But Andromeda isn't the only galaxy out there. There are many more. Our galaxy, the Milky Way, is part of something called the Local Group. This is a collection of about 54 galaxies that are gravitationally bound together. They're moving through space as a group. The Local Group includes the Milky Way, Andromeda, the Triangulum Galaxy, and many smaller galaxies. The Local Group spans about 10 million light-years across. That's the size of our cosmic neighborhood. But beyond the Local Group there are galaxy clusters. These are collections of hundreds or thousands of galaxies. And beyond galaxy clusters, there are superclusters. These are collections of galaxy clusters. The structures get bigger and bigger. Between these structures, there are cosmic voids. These are vast regions of space that are almost completely empty. They can be hundreds of millions of light-years across. They contain very few galaxies. They're like cosmic deserts, empty spaces between the galaxy clusters. The observable universe, the part we can see, is about 93 billion light-years across. It contains about 2 trillion galaxies. That's 2 trillion galaxies. Each with billions of stars, each potentially containing planets. The scale is almost incomprehensible. But here's something interesting. The universe is expanding. Galaxies are moving away from each other. The farther away a galaxy is, the faster it's moving away. This is because space itself is expanding. It's not that galaxies are moving through space, it's that space itself is getting bigger. This expansion was discovered by astronomer Edwin Hubble in the 1920s. He noticed that distant galaxies were all moving away from us. And the farther away they were, the faster they were moving. This became known as Hubble's law. The universe is expanding in all directions, like a balloon being inflated. The rate of expansion is measured by something called the Hubble constant. Current measurements suggest that for every million parsecs of distance, galaxies are moving away at about 70 kilometers per second. A parsec is about 3.26 light-years. So galaxies that are 3.26 million light-years away are moving away at 70 kilometers per second. Galaxies that are twice as far are moving away twice as fast. However, there's actually a discrepancy in measurements of the Hubble constant. Measurements based on the cosmic microwave background, the afterglow of the Big Bang, suggest a value of about 67 kilometers per second per megaparsec. But measurements based on observations of nearby stars and supernovas suggest a value of about 73 kilometers per second per megaparsec. This discrepancy, known as the Hubble tension, is one of the biggest mysteries in cosmology today. It might indicate new physics beyond our current understanding, or it might be due to systematic errors in measurements. Either way, it shows that our understanding of cosmic expansion is still evolving. The expansion rate isn't constant over time either. In the early universe, expansion was slowing down due to gravity. But about 5 billion years ago, something called dark energy began to dominate, causing expansion to accelerate. Dark energy is even more mysterious than dark matter. We don't know what it is, but we can see its effects. It makes up about 68% of the universe's energy density. Dark matter makes up about 27%. Regular matter, everything we can see and touch, makes up only about 5%. So when we talk about the universe, we're really talking about something mostly made of things we don't understand. This expansion has profound implications for intergalactic travel. As we try to reach a distant galaxy, space is expanding between us and it. The galaxy is getting farther away. It's like trying to walk up a down escalator. You're moving forward, but the escalator is moving backward. And the farther away the galaxy is, the faster space is expanding. This expansion makes intergalactic travel even more challenging. As we try to reach a distant galaxy, space is expanding between us and it. The galaxy is getting farther away. It's like trying to walk up a down escalator. You're moving forward, but the escalator is moving backward. And the farther away the galaxy is, the faster space is expanding. For nearby galaxies like Andromeda, this isn't a problem. Andromeda is actually moving toward us, not away. It's on a collision course with the Milky Way. In about 4.5 billion years, the two galaxies will collide and merge. They'll become one larger galaxy. But that's a different story. For galaxies beyond our local group, the expansion of the universe becomes important. Very distant galaxies are moving away from us faster than the speed of light. This doesn't violate the laws of physics, because it's space itself that's expanding, not the galaxies moving through space. But it does mean we could never reach those galaxies, even if we could travel at light speed. They're moving away too fast. So when we talk about intergalactic travel, we're really talking about traveling to nearby galaxies. Galaxies in our local group. Galaxies that aren't moving away from us too fast. Galaxies like Andromeda and Triangulum. Even these nearby galaxies are incredibly far away. But they're at least theoretically reachable. The Triangulum galaxy is the third largest galaxy in our local group. It's about 2.7 million light-years away. Slightly farther than Andromeda, it's smaller than both the Milky Way and Andromeda, but it's still enormous. It contains about 40 billion stars. It's a spiral galaxy, like the Milky Way, with beautiful spiral arms filled with young, bright stars. Triangulum, also known as M33, is actually visible to the naked eye under very dark skies, though it's much fainter than Andromeda. It spans about 60,000 light-years across, smaller than the Milky Way's 100,000 light-years, but still substantial. Recent observations from the Hubble Space Telescope have revealed that Triangulum contains about 25 billion solar masses of stars, plus additional mass in gas and dark matter. Triangulum is interesting because it's actively forming stars. The galaxy has a high star formation rate, with new stars being born at about 0.45 solar masses per year. That's higher than the Milky Way's rate of about 0.68 to 1.45 solar masses per year. But Triangulum is smaller, so it's forming stars more intensively. The galaxy's spiral arms are filled with bright, young star clusters and nebulae, where new stars are being born. Triangulum is also moving toward Andromeda, and some simulations suggest it might collide with Andromeda before Andromeda collides with the Milky Way. This would create a complex three-galaxy merger, though that's billions of years in the future. For intergalactic travel, Triangulum represents another nearby destination, slightly farther than Andromeda, but still within our local group. Beyond the local group, the distances become even more vast. The nearest large galaxy cluster is the Virgo cluster, about 54 million light-years away. It contains over 1,000 galaxies. The distances are so large that even light takes millions of years to travel them. For intergalactic travel, these distances are almost unimaginable. The Great Attractor is a mysterious gravitational anomaly, about 150 million light-years away. It's pulling galaxies toward it, including our own local group. We don't know what it is. It might be a supercluster of galaxies, it might be something else entirely. But it shows that there are structures in the universe that span hundreds of millions of light-years. The observable universe extends about 46.5 billion light-years, in every direction from Earth. That's because the universe has been expanding for 13.8 billion years. The light from the most distant galaxies has been traveling for almost the entire age of the universe, When we look at those galaxies, we're seeing them as they were billions of years ago. But most of those galaxies are moving away from us faster than the speed of light, due to the expansion of space. We could never reach them, even if we could travel at light speed. They're forever beyond our reach. So when we talk about intergalactic travel, we're really talking about nearby galaxies. Galaxies in our local group. Galaxies that aren't moving away too fast. So the scale of intergalactic space is vast. Almost unimaginably vast. The distances are measured in millions of light years. The time it would take to travel those distances with current technology is measured in billions of years. It seems impossible. But is it? That's what we'll explore tonight. The key difference between interstellar travel and intergalactic travel is scale. Interstellar travel means traveling between stars within our galaxy. The nearest star to the Sun is Proxima Centauri, about 4.24 light-years away. With current technology, reaching it would take about 75,000 years. That's a long time, but it's not billions of years. Intergalactic travel means traveling between galaxies. The nearest galaxy is Andromeda, 2.5 million light-years away. That's about 590,000 times farther than Proxima Centauri. The scale difference is enormous. The challenges are correspondingly enormous. But scale is just one challenge. There are others. The physics barriers, the energy requirements, the biological challenges, the timescales. All of these make intergalactic travel seem impossible. But scientists have been thinking about solutions, theoretical solutions. Solutions that might one day become reality. As we drift deeper into this exploration, keep in mind the scale, keep in mind the distances, keep in mind that we're talking about traveling millions of light years. Not thousands, not hundreds of thousands, millions. It's a journey that would take millions of years, even at speeds approaching light speed. But maybe, just maybe, there are ways to make it possible. The scale of intergalactic space reminds us of our place in the universe. We're on a small planet, orbiting an average star, in an average galaxy, among trillions of galaxies. The universe is vast, almost incomprehensibly vast. But that vastness also represents possibility. It represents the potential for exploration, for discovery, for becoming something more than we are now. So as we continue, remember the scale. Remember that we're talking about distances so large they're hard to imagine, timescales so long they're hard to comprehend. But also remember that humans have a history of doing the impossible. We've flown, we've reached space, we've landed on the moon. We've sent probes to every planet in our solar system. Maybe intergalactic travel is next. Maybe it's just a matter of time. Chapter 2: Current Space Travel Capabilities. Before we can understand when intergalactic space travel might become possible, we need to understand where we are now. What can we do today? What are our current capabilities? And why aren't they enough for intergalactic travel? Let's start with the fastest things humans have ever built. The Parker Solar Probe, launched by NASA in 2018, is currently the fastest spacecraft ever created. At its closest approach to the Sun, it reaches speeds of about 430,000 miles per hour, or about 192 kilometers per second. That's fast, really fast. It's about 0.064% of the speed of light. Still very slow compared to light speed, but fast for us. The Parker Solar Probe achieves these speeds by using the Sun's gravity. It swings close to the Sun, using gravity like a slingshot to accelerate. This is called a gravity assist. It's a clever way to gain speed without using fuel. The probe will make 24 close approaches to the Sun over its 7-year mission, each time getting closer and faster. At its closest, it will be just 3.83 million miles from the Sun's surface. That's about 4% of the distance from Earth to the Sun. At that distance, temperatures reach 500 degrees Fahrenheit, hot enough to melt steel. The probe is protected by a 4.5-inch thick carbon composite heat shield that keeps the instruments at a comfortable 85 degrees Fahrenheit. The Parker Solar Probe's mission is to study the Sun's corona, its outer atmosphere, and the solar wind. But its speed records show what's possible with current technology. Even at these incredible speeds, the Parker Solar Probe would take tens of thousands of years to reach the nearest star. To reach Proxima Centauri in 50 years, we'd need to travel at about 8.5% of light speed, which is about 133 times faster than the Parker Solar Probe's maximum speed. Voyager 1, launched in 1977, is currently the farthest human-made object from Earth. It's traveling at about 38,000 miles per hour, or about 17 kilometers per second. That's much slower than the Parker Solar Probe. But Voyager 1 has been traveling for over 45 years. As of 2024, it's about 15 billion miles away from Earth, or about 162 astronomical units. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. Voyager 1 is still sending signals back to Earth, though its power is dwindling. The signals take about 22 hours to reach us, traveling at the speed of light. The spacecraft's radio transmitter operates at just 23 watts, about the power of a refrigerator light bulb. By the time those signals reach Earth, they're incredibly weak. NASA's Deep Space Network uses antennas up to 230 feet across to detect them. The signal strength is about 20 billion times weaker than a digital watch battery. Voyager 1 crossed the heliopause in 2012, the boundary where the solar wind from our Sun gives way to interstellar space. But it's still within the Oort cloud, a vast shell of icy objects that surrounds the solar system. The Oort cloud extends from about 2,000 to 200,000 astronomical units from the Sun. Voyager 1 won't exit the Oort cloud for about 300 years, and it will take about 30,000 years to completely leave the solar system. Even then, it will still be influenced by the Sun's gravity, though that influence will be extremely weak. Voyager 1 carries a golden record, a phonograph record containing sounds and images selected to portray the diversity of life and culture on Earth. It's designed to last billions of years. If intelligent aliens ever find it, they'll hear greetings in 55 languages, sounds of nature and music from around the world. But the chances of anyone finding it are astronomically small. In 40,000 years, Voyager 1 will pass within 1.6 light-years of a star called Gliese 445. But by then, its power will be long gone, and it will be a silent artifact, drifting through space. New Horizons, which flew past Pluto in 2015, is traveling at about 36,000 miles per hour. It's now exploring the Kuiper Belt, the region beyond Neptune filled with icy objects. But like Voyager 1, it's still within our solar system. It will take tens of thousands of years to reach the nearest star. So our current capabilities are limited. We can reach incredible speeds compared to everyday life. But compared to the distances between stars and galaxies, we're moving at a crawl. We're like snails trying to cross a continent. We're moving but so slowly that the journey seems impossible. The problem is propulsion. How do we push spacecraft through space? Currently we use rockets. Rockets work by burning fuel. They throw hot gas out the back, and that pushes the rocket forward. It's like throwing things off a boat to make it move. The more things you throw, the faster you go. But you run out of things to throw. This is called the rocket equation. It was developed by Konstantin Tsiolkovsky, a Russian scientist, in 1903. The rocket equation tells us something important. To go faster, you need more fuel. But more fuel makes the rocket heavier. A heavier rocket needs more fuel to accelerate. It's a cycle. The more you want to go, the more fuel you need. But the more fuel you have, the heavier you are, so you need even more fuel. The rocket equation is expressed mathematically as delta V equals the exhaust velocity times the natural logarithm of the mass ratio. Delta V is the change in velocity you want to achieve. Exhaust velocity is how fast the propellant is ejected. The mass ratio is the total mass divided by the final mass after burning fuel. This equation shows why space travel is so difficult. To double your speed, you need exponentially more fuel. For example, the Saturn V rocket that sent astronauts to the Moon weighed about 6.5 million pounds at launch. But only about 100,000 pounds of that was the actual spacecraft, the rest was fuel. To reach Earth orbit, the Saturn V needed about 96% of its mass to be fuel. To escape Earth's gravity entirely, and reach other planets, you need even more fuel. This is why most rockets are multi-stage. They drop empty fuel tanks as they go, reducing mass and making the remaining fuel more effective. For intergalactic travel, the rocket equation becomes even more challenging. To reach even 10% of light speed, you'd need a mass ratio of about 10 to the 13th power, meaning you'd need 10 trillion times more fuel than payload. That's clearly impossible with chemical rockets. You'd need propulsion systems with much higher exhaust velocities, or systems that don't rely on carrying fuel at all. This is why rockets are mostly fuel. A typical rocket might be 90% fuel by weight. Only 10% is the actual spacecraft. And most of that fuel is used just to get into orbit around Earth. To go farther, you need even more fuel. But you can't carry infinite fuel. There's a limit. Chemical rockets, the kind we use today, are also limited by the energy they can release. Chemical reactions can only release so much energy. Burning hydrogen and oxygen releases a lot of energy, but it's still limited. To reach the speeds needed for interstellar or intergalactic travel, we'd need something much more powerful. Let's think about what it would take to reach Proxima Centauri, the nearest star. It's 4.24 light-years away. With current rocket technology, it would take about 75,000 years to get there. That's assuming we could accelerate continuously, which we can't. In reality, rockets burn their fuel quickly, then coast, so the journey would take even longer. To reach Proxima Centauri in a human lifetime, say 50 years, we'd need to travel at about 8.5% of the speed of light. That's about 16 million miles per hour. Our fastest spacecraft travel at about 430,000 miles per hour. So we'd need to go about 37 times faster. That's a huge increase. But Proxima Centauri is just the nearest star. It's still within our galaxy. To reach Andromeda, the nearest galaxy, we'd need to travel 2.5 million light-years. With current technology, that would take about 50 billion years. That's longer than the universe has existed. Even if we could travel at 10% of the speed of light, which is incredibly fast, it would still take 25 million years to reach Andromeda. That's 25 million years. Humans have only existed for about 200,000 years. So the journey would take 125 times longer than humans have existed. The problem is exponential. As you try to go faster, you need exponentially more energy. To double your speed, you need 4 times the energy. To triple your speed, you need 9 times the energy. The energy requirements grow faster than the speed. This is because of Einstein's theory of relativity. As you approach the speed of light, your mass increases. It takes more and more energy to accelerate. To reach 50% of the speed of light, you'd need an enormous amount of energy. To reach 90%, you'd need even more. To reach 99%, you'd need more energy than exists on Earth. The closer you get to light speed, the harder it becomes to go faster. But here's something interesting. Even if we could reach 99% of the speed of light, the journey to Andromeda would still take 2.5 million years from Earth's perspective. That's because light itself takes 2.5 million years to travel that distance. You can't travel faster than light. That's the ultimate speed limit. However, from the traveler's perspective, time would pass differently. This is called time dilation. It's a strange effect of relativity. If you could travel at 99% of the speed of light, time would slow down for you. A journey that takes 2.5 million years from Earth's perspective might only take a few 100,000 years from your perspective. Still a long time, but less than millions of years. But even with time dilation, the journey would be incredibly long. And we can't even reach 99% of the speed of light with current technology. We can't even reach 1%. We're stuck at 0.064% with our fastest spacecraft. So current space travel capabilities aren't enough for intergalactic travel. They're not even enough for interstellar travel. They're barely enough for exploring our own solar system. We can send probes to planets. We can orbit Earth. We can land on the moon. But we can't reach other stars, let alone other galaxies. This doesn't mean intergalactic travel is impossible. It just means we need different technology. We need propulsion systems that don't rely on chemical rockets. We need ways to generate enormous amounts of energy. We need ways to travel faster, or to make the journey shorter, or to make time pass differently. Scientists have been thinking about these problems for decades. They've proposed theoretical solutions: nuclear propulsion, antimatter engines, solar sails, wormholes, warp drives, generation ships. Each solution has its own challenges. Each has its own possibilities. But before we explore those solutions, we need to understand the physics barriers. Why is it so hard to travel fast? What are the fundamental limits? What does physics tell us about what's possible and what's not? As we continue our journey, remember where we are now. We can travel at 430,000 miles per hour. That's fast for us, but slow for the universe. We can reach planets in our solar system. But we can't reach other stars. We can't reach other galaxies. Not yet. But maybe someday. Maybe with the right technology. Maybe with the right understanding of physics. The gap between what we can do and what we need to do is enormous. But humans have a history of bridging enormous gaps. We've gone from walking to flying. From Earth to the moon. From our solar system to the edge of it. Maybe the next step is to other stars. And maybe, eventually, to other galaxies. But first, we need to understand the physics. We need to understand why it's so hard. We need to understand what might be possible and what might not be. That's what we'll explore next. Chapter 3: The Physics Barriers. The universe has rules, physical laws that govern how everything works. These laws tell us what's possible and what's not. When it comes to intergalactic travel, these laws create barriers. Barriers that seem insurmountable. But understanding these barriers is the first step to finding ways around them. The most fundamental barrier is the speed of light. Light travels at 186,282 miles per second. That's fast. Really fast. Light can circle Earth 7 times in 1 second. It can travel from the Sun to Earth in about 8 minutes. It can travel from the Sun to Pluto in about 5 hours. But here's the thing. Nothing can travel faster than light. Not matter, not information, not energy, nothing. This is one of the most fundamental rules of physics. It's been tested countless times. It's been confirmed by experiments. It seems to be an absolute limit. Why is there a speed limit? The answer lies in Einstein's theory of relativity. Published in 1905, special relativity tells us something profound about space and time. They're not separate, they're connected. They form something called spacetime. And the speed of light is the speed limit of spacetime itself. When you move through space, you also move through time. The faster you move through space, the slower you move through time. This is called time dilation. It's a strange effect, but it's real. It's been measured. Atomic clocks on fast-moving aeroplanes run slightly slower than clocks on the ground. The effect is tiny, but it's there. The most famous test of time dilation was the Hafele-Keating experiment in 1971. Physicists Joseph Hafele and Richard Keating flew atomic clocks around the world on commercial airliners. When they compared these clocks to identical clocks that stayed on the ground, they found that the traveling clocks ran slower, exactly as Einstein's theory predicted. The difference was tiny, just nanoseconds, but it was measurable and matched the predictions perfectly. More recently, scientists have tested time dilation using particle accelerators. Muons, unstable particles that normally decay in microseconds, live longer when accelerated to near-light speeds. At 99.94% of light speed, muons live about 29 times longer than stationary muons. This isn't because the muons themselves change. It's because time passes more slowly for them. From our perspective, their internal clocks run slower. GPS satellites provide another practical demonstration of time dilation. These satellites orbit Earth at about 700 miles per hour. Due to time dilation, their atomic clocks run about 7 microseconds slower per day than clocks on Earth. But GPS satellites are also farther from Earth's gravity, which makes time run faster, an effect called gravitational time dilation. The net effect is that GPS clocks run about 38 microseconds faster per day. If GPS systems didn't account for this, navigation errors would accumulate at about 6 miles per day. Your phone's GPS wouldn't work without Einstein's equations. As you approach the speed of light, time slows down more and more. At 99% of the speed of light, time passes about 7 times slower for you than for someone standing still. At 99.9%, time passes about 22 times slower. The closer you get to light speed, the more time slows down. But here's the catch. As you try to go faster, your mass increases. This is also part of relativity. The faster you move, the heavier you become. At 90% of the speed of light, your mass is about 2.3 times your normal mass. At 99%, it's about 7 times. At 99.9%, it's about 22 times. This means it takes more and more energy to accelerate. The closer you get to light speed, the more energy you need. To reach 50% of the speed of light, you need a certain amount of energy. To reach 90%, you need about 3 times more energy. To reach 99%, you need about 7 times more energy. The energy requirements grow exponentially. To double your speed, you need 4 times the energy. To triple your speed, you need 9 times the energy. This is why it's so hard to go fast. The energy requirements become enormous. Let's think about what it would take to accelerate a small spacecraft to 99% of the speed of light. Say the spacecraft weighs 1,000 kilograms, about the weight of a small car. To accelerate it to 99% of light speed, you'd need energy equivalent to about 6.3 times the mass of the spacecraft converted entirely to energy. This is where Einstein's famous equation comes in. E equals mc squared, energy equals mass times the speed of light squared. This tells us that mass and energy are equivalent. A small amount of mass can be converted into an enormous amount of energy. To accelerate our 1,000 kilogram spacecraft to 99% of light speed, we'd need to convert about 300 kilograms of matter entirely into energy. That's more than 6 times the mass of the spacecraft itself, and that's just to reach 99% of light speed. To reach 99.9%, we'd need even more. But here's the problem. Even at 99% of the speed of light, the journey to Andromeda would still take 2.5 million years from Earth's perspective. That's because light itself takes 2.5 million years to travel that distance. You can't travel faster than light, so you can't get there faster than light can. However, from the traveler's perspective, time would pass differently. Due to time dilation, a journey that takes 2.5 million years from Earth's perspective might only take about 350,000 years from the traveler's perspective. Still an incredibly long time, but less than millions of years. But even 350,000 years is far longer than a human lifetime. Even with time dilation, the journey would take hundreds of thousands of years, and we can't even reach 99% of the speed of light with current technology. We're stuck at 0.064%. The Parker Solar Probe reaches 0.064% of light speed. That's our current limit. To reach even 1% of light speed, we'd need to go about 15 times faster. To reach 10%, we'd need to go about 150 times faster. To reach 50%, we'd need to go about 750 times faster. The gap between what we can do and what we need to do is enormous. But maybe that gap isn't as insurmountable as it seems. Technology develops in unexpected ways. 100 years ago, we couldn't fly. 50 years ago, we couldn't reach space. Today, we can. Maybe in another 100 years, we'll have propulsion systems we can't even imagine today. Maybe the gap will close faster than we think. Or maybe it won't. Maybe we'll hit fundamental limits. Maybe chemical rockets are as good as it gets. Maybe we'll never develop better propulsion. We don't know. The future is uncertain. But the possibility remains. The potential remains. And that's worth exploring. So the physics barriers are significant. The speed of light is an absolute limit. Nothing can travel faster. To approach light speed requires enormous amounts of energy. And even at near light speeds, intergalactic journeys take hundreds of thousands or millions of years. But wait, what if we could travel faster than light? What if we could break the light barrier? Scientists have thought about this. They've explored theoretical possibilities. But so far, every attempt to find a way around the light speed limit has run into problems. One idea is to use wormholes. These are theoretical tunnels through space-time. They could connect two distant points, allowing you to travel between them instantly. You'd enter one end of the wormhole and exit the other, even if they're millions of light years apart. But wormholes have problems. First, they're purely theoretical. We've never observed one. Second, they would require exotic matter with negative energy to stay open. We don't know if such matter exists. Third, even if wormholes exist, they might be unstable. They might collapse before you could travel through them. Another idea is the Alcubierre warp drive. Proposed by physicist Miguel Alcubierre in 1994, this would contract space-time in front of a spacecraft and expand it behind. The spacecraft itself wouldn't move faster than light through space. Instead, space itself would move, carrying the spacecraft along. This is like being on a moving walkway at an airport. You're not walking faster than normal, but the walkway is moving, so you're moving faster overall. The warp drive would do something similar with space-time itself. But the warp drive also has problems. It would require enormous amounts of negative energy. More negative energy than might exist in the entire universe. It might also create dangerous radiation. And it's purely theoretical, we don't know if it's actually possible. So the physics barriers remain. The speed of light seems to be an absolute limit. Wormholes and warp drives are theoretical possibilities, but they have their own problems. They might not be possible at all. But this doesn't mean intergalactic travel is impossible, it just means we need to think differently. Maybe we can't travel faster than light. But maybe we can make the journey shorter, or maybe we can make time pass differently, or maybe we can send something that doesn't need to arrive quickly. Scientists have proposed many solutions. Some are more realistic than others. Some might be possible with future technology. Some might be possible with technology we can't even imagine yet. But all of them face the same fundamental barrier, the speed of light. As we continue our exploration, we'll look at these solutions, we'll see what might be possible, we'll see what challenges they face, and we'll see when they might become reality. But always remember, the physics barriers are real, they're not going away. Any solution must work within the laws of physics, or find a way to bend them. The speed of light is the ultimate speed limit. But maybe that's okay. Maybe we don't need to travel faster than light. Maybe we just need to travel fast enough. Or maybe we need to think about the journey differently. Maybe the journey itself isn't the problem. Maybe the problem is how we think about time, or distance, or what it means to travel. As you drift deeper into sleep, remember that physics has rules, but those rules also create possibilities. They tell us what we can't do, but they also tell us what we might be able to do. The barriers are real, but so are the solutions. We just need to find them. Chapter 4, Theoretical Solutions. Part 1, Propulsion. So we've established the barriers. The distances are vast. The speeds are limited. The energy requirements are enormous. But scientists haven't given up. They've been thinking about solutions, theoretical solutions that might one day make intergalactic travel possible. Let's start with propulsion. How do we push spacecraft faster? Current chemical rockets aren't enough. We need something more powerful, something that can generate more thrust, something that can accelerate for longer, something that doesn't run out of fuel so quickly. One idea is nuclear propulsion. Instead of burning chemical fuel, we could use nuclear reactions. Nuclear reactions release much more energy than chemical reactions. A single gram of nuclear fuel can release as much energy as burning tons of chemical fuel. That's a huge difference. There are two main types of nuclear propulsion: nuclear fission and nuclear fusion. Fission means splitting atoms apart. Fusion means combining atoms together. Both release enormous amounts of energy. Both could potentially power spacecraft. Nuclear fission is what we use in nuclear power plants today. We split uranium atoms, and that releases energy. We could do the same thing in space. We could use nuclear reactors to heat propellant, creating hot gas that pushes the spacecraft forward. This is called nuclear thermal propulsion. NASA has been studying nuclear thermal propulsion for decades. In the 1960s, they tested nuclear rocket engines as part of Project Rover and Project NERVA, nuclear engine for rocket vehicle application. Between 1955 and 1973, they built and tested 23 nuclear rocket engines. The engines worked. They produced more thrust than chemical rockets, with specific impulses of 800 to 900 seconds, about twice that of chemical rockets. But the program was cancelled in 1973. Partly because of safety concerns. Partly because we didn't have a mission that needed it. Partly because of budget cuts. The NERVA engines used nuclear fission to heat liquid hydrogen propellant to temperatures of about 500 degrees Celsius. The hot hydrogen would expand and be ejected through a nozzle, creating thrust. The engines were tested on the ground in Nevada, running for up to 62 minutes at full power. They proved that nuclear thermal propulsion was technically feasible. Today, NASA is reviving interest in nuclear thermal propulsion. The agency's Space Technology Mission Directorate is funding research into new nuclear propulsion systems. One concept, called DRACO, Demonstration Rocket for Agile Cislunar Operations, aims to test a nuclear thermal rocket in space by 2027. These new designs use low-enriched uranium, making them safer than the highly enriched uranium used in the 1960s. But nuclear thermal propulsion could potentially reach speeds of 5 to 10% of light speed. That's still not enough for intergalactic travel, but it's much better than chemical rockets. It could make interstellar travel more feasible. A nuclear thermal rocket could reach Mars in about 3 months instead of 7 months. It could reach the outer planets in years, instead of decades. And it's technology we understand. We know how to build nuclear reactors. We know how to make them work in space. The International Space Station has been powered by solar panels, but future deep space missions might need nuclear power. Nuclear fusion is even more powerful. Fusion is what powers the sun. Hydrogen atoms combine to form helium, releasing enormous amounts of energy. If we could harness fusion for propulsion, we could potentially reach much higher speeds. Maybe 10 to 20% of light speed, maybe more. But fusion is harder than fission. We haven't mastered controlled fusion yet. We can make fusion bombs, but we can't make fusion reactors that produce more energy than they consume. Scientists are working on it. They're building experimental fusion reactors. But we're not there yet. Maybe in 50 years. Maybe in 100 years. Maybe never. The challenge with fusion is that atomic nuclei are positively charged, so they repel each other. To overcome this repulsion and fuse nuclei together, you need extremely high temperatures, about 100 million degrees Celsius, or about 10 times hotter than the sun's core. At these temperatures, matter becomes plasma, a state where electrons are stripped from atoms. You also need to contain this plasma long enough for fusion to occur, which is difficult because hot plasma wants to expand and cool. The most promising approach is magnetic confinement fusion, using devices called tokamaks. These use powerful magnetic fields to contain the plasma in a donut-shaped chamber. The largest tokamak project is ITER, the International Thermonuclear Experimental Reactor, being built in France. ITER is designed to produce 500 megawatts of fusion power from 50 megawatts of input power, a 10-fold gain. But ITER won't be operational until at least 2035, and it's just an experiment. A commercial fusion power plant is still decades away. Another approach is inertial confinement fusion, where powerful lasers compress a tiny pellet of fusion fuel. The National Ignition Facility in California achieved a major breakthrough in 2022, producing more fusion energy than the laser energy used to trigger it, though the total energy input was still much greater than the fusion output. This was a significant milestone, but we're still far from practical fusion power. For space propulsion, fusion has additional challenges. You'd need to miniaturize fusion reactors, make them reliable enough for long missions, and find ways to use the fusion energy for propulsion. Some concepts propose using fusion reactions to heat propellant directly, similar to nuclear thermal rockets. Others propose using fusion to generate electricity for ion drives or other electric propulsion systems. But all of these are still theoretical. We need to master fusion on Earth first, before we can use it in space. Another idea is antimatter propulsion. Antimatter is like regular matter, but with opposite charge. When matter and antimatter meet, they annihilate each other. They convert entirely into energy. This is the most efficient reaction possible. 100% of the mass becomes energy, no waste. If we could produce and store antimatter, we could use it as fuel. We could mix it with regular matter, and the annihilation would create enormous amounts of energy. This energy could heat propellant, or be converted directly into thrust. Antimatter engines could potentially reach speeds of 50% of light speed or more. But antimatter has problems. First, it's incredibly difficult to produce. We can make tiny amounts in particle accelerators, but it costs billions of dollars per gram. The Large Hadron Collider at CERN produces about 10 billion antiprotons per hour, but that's only about 1.67 nanograms per hour. At that rate, it would take billions of years to produce a single gram. And the cost? Estimates range from $25 billion to $62.5 trillion per gram, depending on the production method. Second, it's incredibly difficult to store. Antimatter annihilates when it touches regular matter, so we'd need special containers that use magnetic fields to keep it suspended in a vacuum. Even a single atom of regular matter would cause annihilation. The most successful antimatter storage experiment, conducted at CERN in 2011, stored 309 antihydrogen atoms for about 16 minutes. That's progress, but we'd need to store trillions of times more for a spacecraft. Third, producing enough antimatter for a spacecraft would require enormous amounts of energy. To produce 1 gram of antimatter, you'd need to convert at least 1 gram of matter into energy. That's about 21.5 kilotons of TNT equivalent, or about the energy of a small nuclear bomb. But due to inefficiencies, you'd actually need much more energy input than you'd get from the antimatter. We'd need to build power plants just to make the fuel. Some estimates suggest we'd need a Dyson sphere or similar megastructure to produce antimatter in useful quantities. However, there might be natural sources of antimatter. Some scientists think that antimatter might be produced in the magnetospheres of planets like Jupiter, where high-energy particles could create antimatter. The Pamela satellite detected antiprotons in Earth's magnetosphere, but these are tiny amounts. We're far from mining antimatter from space. For now, antimatter propulsion remains purely theoretical, but if we could solve the production and storage problems, it could be the most efficient propulsion system possible. A spacecraft using antimatter could potentially reach 50% of light speed or more, making interstellar travel feasible, and intergalactic travel at least conceivable. Still, antimatter propulsion is theoretically possible. If we could solve the production and storage problems, it could be the key to fast space travel. Some scientists think we might be able to produce antimatter more efficiently in the future, maybe by mining it from space, maybe by building better particle accelerators, maybe by finding natural sources we don't know about yet. Another idea is solar sails. These are huge, thin sheets that catch light from stars. Light has momentum. When light hits something, it pushes on it. It's a tiny push, but it's constant. Over time, a solar sail could accelerate to high speeds. And it doesn't need fuel. It just needs sunlight. Solar sails are already being tested. In 2010, Japan's Icaros spacecraft successfully deployed a solar sail. Icaros, interplanetary kite craft accelerated by radiation of the sun, had a sail about 46 feet across. It used the pressure of sunlight to accelerate, proving that solar sailing works. Icaros traveled to Venus, demonstrating that solar sails could be used for interplanetary missions. In 2019, the Planetary Society's LightSail 2 demonstrated solar sailing in Earth orbit. LightSail 2 had a sail about 344 square feet, roughly the size of a boxing ring. Over its mission, it raised its orbit by about 2 miles using only sunlight. The sail was made of mylar, a material thinner than a human hair. LightSail 2 showed that solar sailing could work for small spacecraft, though it was limited by atmospheric drag in low Earth orbit. NASA is planning more ambitious solar sail missions. The Advanced Composite Solar Sail System, scheduled for launch in 2025, will test a new sail design made of flexible polymer and carbon fiber. The sail will be about 860 square feet, larger than Light Sail 2, but still relatively small. Future missions might use sails thousands of feet across. For intergalactic travel, we'd need enormous solar sails, perhaps miles across. And we'd need powerful lasers to push them, since sunlight becomes too weak far from stars. The Breakthrough Starshot project proposes using ground-based lasers with a combined power of 100 gigawatts, about the output of 100 large power plants, to accelerate tiny spacecraft to 20% of light speed. But for larger spacecraft we'd need even more powerful lasers, perhaps powered by orbiting solar power stations or nuclear reactors. The physics of solar sails is fascinating. Photons, particles of light, have momentum even though they have no mass. When photons hit a surface, they transfer momentum, creating pressure. This radiation pressure is tiny, about 9 micronewtons per square meter, at Earth's distance from the Sun. But it's constant and requires no fuel. Over time, this tiny push can accelerate a spacecraft to high speeds. The key is having a large, lightweight sail and enough time for the acceleration to build up. For intergalactic travel, we'd need enormous solar sails, maybe miles across. And we'd need powerful lasers to push them. The Breakthrough Starshot project proposes sending tiny spacecraft to Proxima Centauri using laser-powered light sails. The lasers would be on Earth or in orbit. They'd shine on the sails, accelerating the spacecraft to 20% of light speed in just minutes. But Breakthrough Starshot is designed for tiny probes, not human spacecraft. For intergalactic travel, we'd need much larger sails and much more powerful lasers. We'd need lasers that could push spacecraft for years or decades. That's a huge engineering challenge. But it's theoretically possible. Ion drives are another option. These use electric fields to accelerate ions, creating thrust. They're very efficient. They can run for years on small amounts of fuel, but they produce very little thrust. They're like a gentle breeze pushing a sailboat, slow but steady. NASA's Dawn spacecraft used ion drives to visit the asteroids Vesta and Ceres. It worked. The spacecraft reached its destinations. But it took years. Ion drives are great for long missions within the solar system, but they're too slow for intergalactic travel. They take millions of years to reach even nearby galaxies. The efficiency of ion drives is impressive. They can achieve specific impulses of 3,000 to 10,000 seconds. That's much better than chemical rockets, which achieve only 300 to 450 seconds. Specific impulse measures how efficiently a rocket uses propellant. Higher is better. Ion drives are incredibly efficient, but they're also incredibly slow. What if we made ion drives more powerful? What if we used nuclear power to generate more electricity? What if we built larger ion drives? Maybe we could increase the thrust while keeping the efficiency. Maybe we could accelerate faster. But even then, ion drives would probably be too slow for intergalactic travel. They're better suited for missions within our solar system. But what if we combined ideas? What if we used nuclear power to run ion drives? What if we used fusion to power antimatter production? What if we used multiple propulsion methods together? Maybe the solution isn't one technology, but a combination of technologies. A hybrid system might use nuclear reactors to generate electricity. That electricity could power ion drives for efficient, long-term acceleration. Or it could power other systems. The nuclear reactor would provide the energy. The ion drives would provide the thrust. Together they might be more capable than either alone. The Bussard ramjet is an interesting idea. Proposed by physicist Robert Bussard in 1960, it would scoop up hydrogen from space as it travels. The hydrogen would be used as fuel for fusion reactions. The spacecraft wouldn't need to carry fuel, it would collect it as it goes. The concept is elegant. Instead of carrying fuel, you collect it. You use magnetic fields to gather hydrogen from the interstellar medium. You compress it. You use it for fusion. You accelerate. You collect more hydrogen. You accelerate more. Over time you could reach very high speeds. But the Bussard ramjet has problems. Space is mostly empty. There isn't much hydrogen between stars. The average density of the interstellar medium is about 1 atom per cubic centimeter. That's incredibly sparse. The scoop would need to be enormous, maybe hundreds of miles across, to collect enough hydrogen. And collecting hydrogen would create drag. The scoop would slow the spacecraft down. The drag might be greater than the thrust from fusion. The spacecraft might slow down instead of speeding up. It might not work at all. Some scientists have calculated that a Bussard ramjet might only work at speeds above a certain threshold. Below that speed, drag is too high. Above that speed, thrust might overcome drag, but reaching that threshold speed would require other propulsion methods first. So the ramjet might be useful for maintaining speed, but not for initial acceleration. Still, the idea is interesting. It shows creative thinking. It shows that we can imagine solutions beyond carrying fuel. Maybe there are other ways to collect resources in space. Maybe there are other ways to power spacecraft. Another propulsion idea is the nuclear pulse drive. This was part of Project Orion, studied in the 1950s and 1960s. The idea was to detonate nuclear bombs behind a spacecraft. The explosions would push the spacecraft forward. It sounds dangerous, and it is, but it might work. Project Orion was serious. Scientists calculated that a nuclear pulse drive could potentially reach 3 to 5% of light speed. That's fast enough for interstellar travel, though not fast enough for intergalactic travel. But it's a start. The spacecraft would have a large pusher plate at the back. Nuclear bombs would be ejected and detonated behind it. The explosions would push against the plate, accelerating the spacecraft. Shock absorbers would cushion the acceleration. It would be like riding a series of explosions. The project was cancelled for several reasons: nuclear testing treaties, safety concerns, environmental concerns. But the physics was sound. It might have worked. And it shows that there are creative ways to think about propulsion. Still, these propulsion ideas show that there are possibilities. Nuclear propulsion could work. Antimatter propulsion could work. Solar sails could work. Nuclear pulse drives could work. Maybe not for intergalactic travel right away, but maybe for interstellar travel. And maybe interstellar travel is the first step toward intergalactic travel. The key is finding something that can accelerate continuously. Chemical rockets burn their fuel quickly, then coast. But if we could accelerate continuously, even at a small rate, we could reach high speeds over time. A spacecraft accelerating at just 1 g, the acceleration of Earth's gravity, could reach near-light speeds in about a year. That's if we had a propulsion system that could accelerate continuously. At 1 g acceleration, you'd feel normal gravity. You could walk around normally. You could live normally. And after a year, you'd be traveling at about 77% of the speed of light. After 2 years, you'd be at about 97%. After 3 years, you'd be at about 99.5%. Continuous acceleration is powerful. But continuous acceleration requires continuous thrust. That requires continuous fuel consumption. Or continuous energy input. That's the challenge. How do we maintain acceleration for years? How do we power it? How do we make it efficient? So propulsion is one piece of the puzzle. But it's not the only piece. Even with better propulsion, we still face the speed of light barrier. We still face the energy requirements. We still face the timescales. That's why scientists have also been thinking about more exotic solutions. Solutions that might bypass these problems entirely. Chapter 5. Theoretical Solutions. Part 2. Exotic Concepts. Sometimes the best way to solve a problem is to think about it completely differently. Instead of trying to go faster, what if we could make the distance shorter? Instead of trying to travel through space, what if we could travel through space-time itself? These are the exotic concepts, the ideas that push the boundaries of physics. Let's start with wormholes. These are theoretical tunnels through space-time. They're also called Einstein-Rosen bridges, named after Albert Einstein and Nathan Rosen, who first described them mathematically in 1935. A wormhole would connect two distant points in space. You'd enter one end and exit the other, even if they're millions of light-years apart. Imagine space is like a piece of paper. Normally, to get from one side to the other, you'd travel across the surface. But what if you could fold the paper and poke a hole through it? That's what a wormhole would do. It would create a shortcut through space-time. Wormholes are allowed by Einstein's theory of general relativity. The math says they could exist. But there are problems. First, we've never observed one. They're purely theoretical. Second, they would require exotic matter with negative energy to stay open. Exotic matter would have negative mass, which means it would repel rather than attract. We don't know if such matter exists. Third, even if wormholes exist, they might be unstable. They might collapse before anything could travel through them. They might be microscopic, too small for a spacecraft. They might exist only for tiny fractions of a second. We don't know. Some scientists think wormholes might be created naturally, maybe by black holes. Maybe by the Big Bang. Maybe they're everywhere, but we can't see them. Others think we might be able to create them artificially. But that would require technology far beyond what we have now. It would require manipulating spacetime itself. The Alcubierre warp drive is another exotic idea. Proposed by physicist Miguel Alcubierre in 1994, it would contract spacetime in front of a spacecraft and expand it behind. The spacecraft itself wouldn't move faster than light through space. Instead, space itself would move, carrying the spacecraft along. Think of it like a surfer riding a wave. The surfer isn't moving through the water, the wave is moving, and the surfer rides it. The warp drive would do something similar with spacetime. The spacecraft would ride a wave of spacetime. This is clever because it doesn't violate the speed of light limit. The spacecraft isn't moving faster than light through space. Space itself is moving. And there's no limit on how fast space can expand or contract. But the warp drive has problems. It would require enormous amounts of negative energy. More negative energy than might exist in the entire universe. The original calculations suggested we'd need negative energy equivalent to the mass of Jupiter. That's an enormous amount. We don't even know if negative energy exists, let alone how to produce it. It might also create dangerous radiation. Anyone inside the warp bubble might be exposed to deadly radiation. The radiation could kill everyone on board. Some scientists think the radiation problem might be solvable. Others think it might be fundamental. We don't know yet. And it's purely theoretical. We don't know if it's actually possible. The math says it might be possible, but the math also requires things we're not sure exist. Negative energy, exotic matter. We don't know if these things are real. Some scientists have been working on variations of the warp drive. They've been trying to reduce the energy requirements. Recent calculations suggest we might need less negative energy than originally thought. Maybe only the mass of a small moon instead of Jupiter. That's still enormous, but it's progress. They've been trying to solve the radiation problems. Some think we could shield against it. Others think the radiation might not be as dangerous as feared. But we're still far from building one. Maybe it's impossible, maybe it's just very difficult. We don't know yet. NASA has a small research program studying warp drives. It's called the Eagle Works Laboratory, part of NASA's Johnson Space Center. They're not building warp drives. They're just studying the physics. They're trying to understand if it's possible. They're testing small-scale effects. It's early research, but it shows that scientists are taking the idea seriously. The EagleWorks team, led by physicist Harold White, has been working on variations of the Alcubierre drive since 2010. They've been trying to reduce the energy requirements and solve the radiation problems. In 2014, White proposed a modified design using a torus-shaped warp bubble instead of a flat bubble, which might reduce energy requirements by orders of magnitude. Instead of needing the mass energy of Jupiter, White's design might only need the mass energy of the Voyager 1 spacecraft. Still enormous, but more conceivable. The team has also been testing something called the White-Jude Warp Field Interferometer, a device designed to detect tiny warp field effects in the laboratory. The idea is that if you can create even a microscopic warp bubble, you might be able to measure its effects. So far, no definitive results have been published, but the research continues. Other scientists have been working on warp drive variations. In 2020, physicist Eric Lentz proposed a new type of warp drive that wouldn't require negative energy. Instead, it would use regular matter arranged in a specific configuration. But this design has its own problems. It might require more energy than the entire universe contains, and it might still create dangerous radiation. The fundamental challenge with warp drives is that they require manipulating space-time itself. We don't know if that's possible, or if it would require physics beyond our current understanding. But the research continues, driven by the possibility that warp drives might be the only way to make intergalactic travel practical. If we could build one, we could travel to Andromeda in weeks instead of millions of years. That's a prize worth pursuing, even if the odds are long. The warp drive remains one of the most intriguing possibilities. If it could work, intergalactic travel would become trivial. You could travel to Andromeda in days or weeks instead of millions of years. But we're a long way from knowing if it's possible, let alone building one. Generation ships are a different approach. Instead of trying to go fast, what if we accept that the journey will take a long time? What if we build a ship that can sustain human life for thousands or millions of years? A ship where generations of people are born, live and die during the journey. This is the generation ship concept. It's like a moving city in space. It would need to be self-sufficient. It would need to produce food, recycle air and water, generate power and maintain itself. It would need to support a population large enough to avoid genetic problems. Maybe thousands of people, maybe tens of thousands. The ship would travel slowly, maybe 1 or 2% of light speed. The journey to Andromeda would take millions of years. But that's okay. The people on the ship wouldn't know any different. They'd be born on the ship. They'd die on the ship. Their children would be born on the ship, generation after generation, until finally, millions of years later, the ship arrives at its destination. This is theoretically possible. We know how to build life support systems, we know how to grow food, we know how to recycle resources. The challenge is building a system that can last for millions of years without breaking down. That's the hard part. Cryogenic sleep is another idea. What if we could freeze people and wake them up when we arrive? They'd sleep through the entire journey. Time would pass, but they wouldn't experience it. They'd be frozen, preserved, waiting. We can freeze some things. We freeze sperm and eggs, we freeze embryos. But we can't freeze whole people yet. When we try, ice crystals form and damage cells. We'd need a way to prevent ice formation. Maybe by replacing blood with antifreeze. Maybe by cooling so fast that ice doesn't have time to form. Scientists are working on this. They're studying animals that can survive freezing. Some frogs can freeze solid and come back to life. Some insects can survive extreme cold. Maybe we can learn from them. Maybe we can develop technology to freeze and revive humans. But even if we could freeze people, we'd still need a ship that can travel for millions of years. We'd still need systems that can maintain themselves. We'd still need to solve all the other problems. Cryogenic sleep just changes who experiences the journey, not the journey itself. Digital consciousness transfer is perhaps the most exotic idea. What if we could upload human minds into computers? What if we could send digital copies of ourselves to other galaxies? The journey would take millions of years, but the digital minds wouldn't care. They'd just be data, stored on computers, waiting. This raises profound questions. What is consciousness? Can it be digitized? Would a digital copy be the same person, or just a copy? These are philosophical questions, as much as scientific ones. But if consciousness could be digitized, intergalactic travel would become much easier. We could send tiny probes with computer chips. We could send millions of them. They'd be cheap, they'd be fast, they wouldn't need life support, they'd just need power and memory. Some scientists think this might be possible in the future. As we learn more about the brain, as computers become more powerful, maybe we'll understand consciousness well enough to digitize it. Maybe we'll be able to upload minds. Maybe we'll be able to download them into new bodies at the destination. But we're not there yet. We don't understand consciousness well enough. We don't have computers powerful enough. And we don't know if it's even possible. But it's an interesting idea. It's a way to think about the problem differently. Self-replicating probes are another idea, proposed by mathematician John von Neumann in the 1940s. These would be probes that can build copies of themselves. A single probe arrives at a star system. It mines materials. It builds factories. It builds copies of itself. Then the copies travel to other star systems and do the same thing. The mathematics are compelling. If a probe could replicate itself every 500 years, and each copy could travel to a nearby star system, a single probe could explore the entire Milky Way in just a few million years. That's a blink of an eye on cosmic timescales. For intergalactic travel, self-replicating probes could work similarly. They'd travel to other galaxies. They'd replicate. They'd explore. They'd send information back. They wouldn't need to travel fast. They'd have millions of years. They'd just need to survive and replicate. But self-replicating probes raise concerns. What if they malfunction? What if they start replicating uncontrollably? What if they consume entire star systems? These are risks we'd need to consider. Still, these exotic concepts show that there are many ways to think about intergalactic travel. Maybe we don't need to go fast. Maybe we don't need to travel through space normally. Maybe we can use wormholes or warp drives. Maybe we can send digital minds or self-replicating probes. Maybe the solution is a combination of these ideas. The key is that we're thinking about the problem. We're exploring possibilities. We're pushing the boundaries of what might be possible. And that's important. Because the first step to solving a problem is understanding it. And the second step is imagining solutions, even if they seem impossible now. Chapter 6: Time and Relativity Solutions. There's something strange about relativity, something that might help us with intergalactic travel. It's called time dilation, and it changes how we think about long journeys. Time dilation means that time passes differently for people moving at different speeds. If you're moving very fast, time passes more slowly for you than for someone standing still. This isn't just theory, it's been measured, it's real. Atomic clocks on fast-moving airplanes run slightly slower than clocks on the ground. The effect is tiny, but it's there. GPS satellites have to account for time dilation. Their clocks run slightly faster, because they're moving relative to Earth. If we didn't correct for this, GPS wouldn't work. Your phone's navigation would be off by miles. The faster you go, the more time slows down. At 50% of the speed of light, time passes about 15% slower. At 90%, time passes about 56% slower. At 99%, time passes about 86% slower. At 99.9%, time passes about 97% slower. This means that from the traveler's perspective, long journeys take less time. A journey that takes millions of years from Earth's perspective might only take thousands of years from the traveler's perspective. Still a long time, but much less than millions of years. Let's think about a journey to Andromeda. It's 2.5 million light-years away. Light itself takes 2.5 million years to travel that distance. So from Earth's perspective, even traveling at the speed of light would take 2.5 million years. But what if we could travel at 99.9% of the speed of light? From Earth's perspective, the journey would still take about 2.5 million years. But from the traveler's perspective, due to time dilation, the journey would only take about 75,000 years. That's still a long time, but it's much less than 2.5 million years. What if we could travel at 99.99% of the speed of light? From the traveler's perspective, the journey would only take about 11,000 years. Still long, but getting more manageable. What if we could reach 99.999%? From the traveler's perspective, only about 1/100 years. That's still longer than human history, but it's not millions of years. This is the twin paradox. Imagine two twins. One stays on Earth. One travels to a distant star at near light speed. When the traveling twin returns, they're much younger than the twin who stayed. Time passed more slowly for the traveler. But here's the catch. Time dilation only helps the travelers. For everyone back on Earth, time passes normally. If a spacecraft leaves for Andromeda and takes 2.5 million years to arrive from Earth's perspective, that's how long it takes. Everyone on Earth will be long gone. The Earth itself might be gone, the Sun might have died, everything will have changed. So time dilation doesn't solve the problem of intergalactic travel. It just changes who experiences the journey. The travelers might experience a shorter journey, but Earth still experiences the full time. And we'd need to reach incredibly high speeds for time dilation to help significantly. Speeds we can't reach with current technology. But time dilation does open up possibilities. If we could build generation ships that travel at near light speeds, the people on board would experience a shorter journey. A journey that takes millions of years from Earth's perspective might only take thousands of years from their perspective. That makes generation ships more feasible. It also means that if we could reach very high speeds, maybe 99.9% of light speed or more, intergalactic travel might become possible for the travelers. They'd still need to accept that everyone they knew would be gone. They'd still need to accept that Earth would be completely different when they arrived. But the journey itself might be manageable. There's another strange effect of relativity called length contraction. As you move faster, distances appear shorter. At 99.9% of the speed of light, distances appear about 22 times shorter. So from the traveler's perspective, Andromeda might appear much closer than 2.5 million light-years. It might appear only about 110,000 light-years away. This is because space and time are connected. As time slows down, space contracts. The faster you go, the more space contracts. So from the traveler's perspective, the journey is shorter in both time and distance. But again, this only helps the travelers. From Earth's perspective, nothing changes. The distance is still 2.5 million light-years. The journey still takes 2.5 million years. Relativity doesn't make the journey shorter for Earth. It just makes it shorter for the travelers. So time dilation and length contraction are interesting effects. They show that time and space aren't absolute. They're relative. They depend on how fast you're moving. This is strange, but it's real. It's been measured. It's part of how the universe works. For intergalactic travel, these effects mean that if we could reach very high speeds, the journey might be more manageable for the travelers. But we'd still need to solve all the other problems. We'd still need propulsion systems that can reach those speeds. We'd still need energy sources that can power those systems. We'd still need to accept that Earth would be completely different when we arrive. But maybe that's okay. Maybe the travelers don't care about Earth. Maybe they're building a new civilization. Maybe they're exploring. Maybe they're just going. And maybe, with time dilation, the journey is possible. Not easy, not quick, but possible. As you drift deeper into sleep, remember that time is strange. It's not constant, it's relative. It depends on how fast you're moving. And maybe, just maybe, that strangeness can help us travel between galaxies. Maybe relativity isn't just a barrier. Maybe it's also a tool. A way to make the impossible possible. Chapter 7. The Energy Problem. Even if we could solve all the other problems, we'd still face the energy problem. How do we generate enough energy to power intergalactic travel? The energy requirements are enormous. Almost unimaginably enormous. Let's think about what it would take to accelerate a spacecraft to near light speed. Say we want to reach 99% of the speed of light. For a 1,000 kilogram spacecraft, we'd need energy equivalent to converting about 300 kilograms of matter entirely into energy. That's using Einstein's equation, E=mc². But that's just for a small spacecraft. For a human spacecraft we'd need much more. A generation ship might weigh millions of kilograms. To accelerate it to 99% of light speed, we'd need to convert millions of kilograms of matter into energy. That's an enormous amount of energy. Where would we get it? Currently, humanity uses about 600 exajoules of energy per year, or about 18 terawatts continuously. That's 600 followed by 18 zeros. It's a lot, but it's not enough. To power an intergalactic spacecraft, we'd need much more energy than humanity currently produces. Let's put this in perspective. To accelerate a 1,000-ton spacecraft, about the size of a large ship, to 99% of light speed, we'd need about 6.3 million tons of matter converted entirely to energy. That's using Einstein's E=mc² equation. But that's just for acceleration. We'd also need energy for deceleration, life support, and other systems. A realistic intergalactic spacecraft might need 10 to 100 times more energy than this minimum. The total energy needed might be equivalent to converting 63 million to 630 million tons of matter into energy. To put that in perspective, the largest nuclear bomb ever detonated, the Tsar Bomba, converted about 2.4 kilograms of matter into energy. So we'd need the energy equivalent of about 26 billion to 260 billion Tsar Bombas. That's an almost unimaginable amount of energy. Currently, all of humanity produces about 600 exajoules per year. 1 exajoule is 10 to the power of 18 joules. To accelerate our 1,000-ton spacecraft to 99% light speed, we'd need about 5.7 times 10 to the 23 joules, about 950,000 exajoules. That's about 1/580 years of current global energy production, just for one spacecraft. And that's assuming 100% efficiency, which is impossible. Real systems might be 10 to 50% efficient, making the energy requirements even higher. One idea is to harness the energy of stars. A Dyson sphere is a theoretical structure that would surround a star and capture all its energy. Proposed by physicist Freeman Dyson in 1960, it would be a shell of solar panels around a star. The star would shine, and the panels would collect the energy. The Sun produces about 3.8 times 10 to the 26th power watts of energy. That's 380 septillion watts. It's an enormous amount. Every second, the Sun converts about 4 million tons of matter into energy. That's the mass of a small mountain, converted to energy every second. If we could capture all of that energy, we'd have more energy than we'd know what to do with. Humanity currently uses about 600 exajoules of energy per year. The Sun produces that much energy in just 1 hour. In one day, the Sun produces more energy than humanity has used in its entire history. We could power thousands of spacecraft with that energy. We could accelerate them to near-light speeds. We could send probes to every star in our galaxy. We could potentially become a Type 2 civilization, capable of using all the energy from our star. But capturing all that energy is a huge challenge. A Dyson sphere would need to be enormous. It would need to be about 1 astronomical unit in radius, about 93 million miles from the Sun. That's the distance from Earth to the Sun. The sphere would need to be about 600 million miles in circumference. That's a lot of material. Some estimates suggest we'd need to disassemble entire planets to build a Dyson sphere. We'd need to mine Mercury, maybe Venus, maybe asteroids. Mercury alone has enough material, about 3.3 times 10 to the 23 kilograms, to build a Dyson sphere. But we'd need to process the materials, transport them, and assemble them in space. The construction would be a massive undertaking. Physicist Freeman Dyson originally proposed the concept in 1960, suggesting that advanced civilizations might build such structures to capture stellar energy. A Dyson sphere wouldn't necessarily be a solid shell that would be unstable and impractical. Instead, it might be a swarm of solar collectors orbiting the star, or a ring of collectors, or a partial shell. The key is capturing a significant fraction of the star's energy output. The construction would take thousands of years, maybe millions, but if we could do it, we'd have enough energy for intergalactic travel. With all the Sun's energy at our disposal, we could power thousands of spacecraft, accelerate them to near-light speeds, and send them to other galaxies. A Dyson sphere would mark our transition to a Type 2 civilization, a civilization capable of harnessing all the energy from its star. But building a Dyson sphere is just the beginning. We'd also need to store and transport that energy. We'd need to convert it into form suitable for spacecraft propulsion. We'd need to build the spacecraft themselves, and we'd need to solve all the other problems: propulsion, life support, radiation protection, and more. A Dyson sphere would give us the energy, but it wouldn't solve everything. But building a Dyson sphere is a huge engineering challenge. We'd need materials. We'd need to build it in space. We'd need to maintain it. It might take thousands of years to build. But it's theoretically possible. And if we could build one, we'd have enough energy for intergalactic travel. Another idea is fusion energy. Fusion is what powers stars. If we could build fusion reactors, we could generate enormous amounts of energy. We're working on it. Experimental fusion reactors are being built. But we're not there yet. We can't make fusion reactors that produce more energy than they consume. If we could master fusion, we might be able to power spacecraft directly. We could use fusion reactions to heat propellant, creating thrust. Or we could use fusion to generate electricity, powering other propulsion systems. Fusion could be the key to fast space travel. Antimatter is another energy source. When matter and antimatter annihilate, they convert entirely into energy. It's the most efficient reaction possible. But producing antimatter requires enormous amounts of energy. We'd need to put in more energy than we'd get out. So antimatter isn't really an energy source. It's more like an energy storage method. But if we could produce antimatter efficiently, maybe by harnessing stellar energy or fusion, we could use it as fuel. We could store it, transport it, and use it when needed. Antimatter could be the fuel that powers intergalactic spacecraft. The problem is that we can't produce antimatter efficiently yet. We can make tiny amounts in particle accelerators, but it costs billions of dollars per gram. We'd need to find a way to produce it much more cheaply, maybe by building better particle accelerators, maybe by finding natural sources, maybe by developing new technologies. Energy storage is also a problem. Even if we could generate enormous amounts of energy, how would we store it? Batteries aren't efficient enough, they're too heavy. We'd need something better, maybe antimatter storage, maybe compressed matter, maybe something we haven't thought of yet. Efficiency is another concern. No system is 100% efficient. We lose energy to heat, to friction, to waste. Even the best propulsion systems waste energy. So we'd need to generate more energy than we actually use. The inefficiency makes the problem worse. But maybe we don't need to solve the energy problem all at once. Maybe we can generate energy as we go. Solar sails use sunlight, which is free. Nuclear reactors can run for years on small amounts of fuel. Fusion reactors, if we can build them, could run for even longer. Maybe the solution is to travel slowly. If we don't need to reach near light speeds, we don't need as much energy. A generation ship traveling at 1% of light speed would need much less energy than one traveling at 99%. The journey would take longer, but it might be more feasible. Or maybe the solution is to think about energy differently. Maybe we don't need to carry all the energy with us. Maybe we can collect it along the way. Maybe we can use the energy of stars we pass. Maybe we can use gravitational assists to gain speed without using energy. The energy problem is real, it's significant, but it's not necessarily insurmountable. With better technology, with better understanding, maybe we can solve it. Maybe we can generate enough energy. Maybe we can store it efficiently. Maybe we can use it wisely. As we continue our exploration, remember that energy is just one problem among many, but it's an important one. Without enough energy, intergalactic travel is impossible. With enough energy, it might become possible. The question is, how do we get there? Chapter 8: Biological and Practical Challenges. Even if we could solve all the physics problems, even if we could generate enough energy, we'd still face biological challenges. Humans aren't designed for space travel, we're designed for Earth. We need air, water, food, gravity, protection from radiation. Space has none of these things. Let's start with radiation. Space is filled with cosmic radiation, high-energy particles from the Sun, from other stars, from supernovas. On Earth, we're protected by the atmosphere and magnetic field. In space, we're exposed. Cosmic radiation can damage DNA, cause cancer, harm the brain. It's dangerous. For a journey to Andromeda, even at near light speeds, we'd be exposed to cosmic radiation for thousands or millions of years. We'd need shielding, thick shielding. Maybe meters of material. Water works well, so does lead. But shielding is heavy. Heavy shielding means more fuel. More fuel means more energy. It's a cycle. We'd also need to protect against solar radiation. The sun emits particles that can be deadly. During solar flares, the radiation increases dramatically. A single solar flare can release as much energy as millions of nuclear bombs. The particles travel at nearly the speed of light. They can penetrate shielding. They can damage electronics. They can harm humans. On Earth, we're protected by the atmosphere and magnetic field. In space, we're exposed. Astronauts on the International Space Station are partially protected by Earth's magnetic field. But for an intergalactic journey, we'd be far from any planet's protection. We'd be on our own. We'd need warning systems. We'd need to detect solar flares before they reach us. We'd need safe rooms with extra shielding. We'd need to be prepared to take shelter quickly. We'd need backup systems, in case primary systems fail. Radiation protection would be a constant concern. Cosmic rays are another problem. These are high-energy particles from outside our solar system. They come from supernovas, from black holes, from unknown sources. They're more energetic than solar radiation. They're harder to shield against. They can cause cancer. They can damage the brain. They're a serious threat. Studies show that astronauts on long missions would be exposed to dangerous levels of cosmic radiation. A journey to Mars would expose astronauts to radiation equivalent to getting a CT scan every few days. The total radiation dose for a round trip to Mars might be about 0.6 to 1 Cephet, about 15 to 25% of the lifetime limit recommended for astronauts. For an intergalactic journey lasting millions of years, the exposure would be much worse. We'd accumulate radiation doses thousands of times higher than safe limits. Cosmic rays come in different types. Galactic cosmic rays are high-energy particles, mostly protons, accelerated by supernovas and other cosmic events. They have energies up to 10 to the power of 20 electron volts, millions of times more energetic than particles in the Large Hadron Collider. These particles can penetrate deep into matter, creating secondary particles that cause even more damage. Solar particle events are bursts of radiation from the Sun, especially during solar flares and coronal mass ejections. These events can increase radiation levels by factors of 100 to 1000 for hours or days. The particles are mostly protons and alpha particles, with energies up to several hundred million electron volts. They're less energetic than galactic cosmic rays but more intense during events. Shielding is the main defense, but it's heavy. Water is effective. About 2.5 feet of water can reduce radiation by half. But for a million-year journey, we'd need much more. Some calculations suggest we'd need 10 to 20 feet of water, or equivalent material, to provide adequate protection. For a large spacecraft, that's millions of tons of shielding material. Alternative approaches include magnetic shielding, using powerful magnets to deflect charged particles. But this would require enormous magnetic fields and lots of power. Another idea is to use the spacecraft structure itself as shielding, arranging living spaces in the center, surrounded by storage, fuel tanks, and other mass. But even with the best shielding, some radiation would get through. We'd need to accept some risk, or find ways to repair radiation damage biologically. Then there's the problem of microgravity. Humans need gravity. Without it, bones weaken, muscles atrophy, the heart changes, vision problems develop. Astronauts on the International Space Station experience these effects. After months in space, they need months to recover. For an intergalactic journey, we'd need artificial gravity. We could spin the spacecraft, creating centrifugal force. Or we could accelerate continuously, creating acceleration gravity. But both require energy. Spinning requires power. Continuous acceleration requires constant thrust. Both are challenging. We'd also need life support systems: air, water, food. We'd need to recycle everything. The air we breathe out becomes the air we breathe in. The water we drink becomes the water we drink again. The food we eat needs to be grown, processed, recycled. It's a closed system. Everything must be reused. The International Space Station has life support systems. They recycle about 93% of the water. They're working on recycling air more efficiently. But they're not perfect. and they're designed for a few people for a few years. For an intergalactic journey, we'd need systems that work for thousands of people for thousands of years. We'd need to grow food. Hydroponics, aeroponics, maybe even soil-based systems. We'd need to produce enough food for everyone. We'd need variety. We'd need nutrition. We'd need to prevent crop failures. It's a huge challenge. We'd need medical care. People get sick, people get injured. We'd need doctors, hospitals, medicine. We'd need to treat diseases we've never seen. We'd need to perform surgeries. We'd need to handle emergencies. All in space, far from Earth, with limited resources. We'd need psychological support. People get lonely. People get depressed. People get stressed. Being confined in a spacecraft for thousands of years would be difficult. We'd need mental health care. We'd need activities. We'd need purpose. We'd need hope. We'd need a large population. To avoid genetic problems, we'd need thousands of people, maybe tens of thousands. Genetic diversity is important. Too small a population, and genetic problems accumulate. Inbreeding becomes a problem. Genetic diseases become common. The population becomes unhealthy. Scientists estimate that a minimum viable population for long-term survival is about 10,000 people. That's enough genetic diversity to avoid most problems. This number comes from population genetics research, which studies how genetic diversity is maintained in small populations. Below about 5,000 people, genetic drift, random changes in gene frequencies, become significant. Inbreeding increases, and harmful mutations accumulate. Above 10,000 people, genetic diversity is generally maintained, though the exact number depends on factors like mating patterns, mutation rates, and selection pressures. But for a journey lasting millions of years, we might need more, maybe 50,000 people, maybe 100,000. The exact number depends on many factors. Over millions of years, even large populations will evolve. New mutations will arise. Natural selection will act. The population might split into subgroups. Genetic diversity might increase or decrease, depending on population dynamics. Some researchers have modeled generation ship populations using computer simulations. These models account for factors like birth rates, death rates, mating patterns, genetic mutations, and population bottlenecks. Results vary, but many suggest that populations of 20,000 to 40,000 people would be needed for million-year journeys. Smaller populations might survive but would lose genetic diversity over time. Larger populations would be safer, but require more resources. The population would also need careful management. We'd need to track genetics, prevent inbreeding, ensure genetic diversity is maintained. We'd need family planning, population control, and possibly genetic engineering to introduce beneficial traits, or remove harmful ones. Over millions of years, the population might evolve into something quite different from the original settlers. They might become a new species, adapted to life in space. Each person needs air, water, food, space. Each person produces waste. Each person needs care. The larger the population, the more resources we need. But the larger the population, the more genetic diversity we have. It's a balance. We need enough people for genetic health, but not so many that we can't support them. The population would need to be carefully managed. We'd need to track genetics, we'd need to prevent inbreeding, we'd need to ensure genetic diversity is maintained. We'd need family planning, we'd need population control. It's a complex challenge. We'd also need to maintain culture. Over millions of years, cultures change. Languages evolve. Traditions fade. The people who arrive at Andromeda would be very different from the people who left Earth. They might not even remember Earth. They might not care about Earth. They'd be a new civilization born in space. The Biosphere 2 experiment showed us how difficult closed systems are. In the 1990s, scientists built a sealed environment in Arizona. It was a huge structure, covering 3.14 acres, with a volume of about 7.2 million cubic feet. It contained different ecosystems: rainforest, ocean, desert, savanna, marsh, and agricultural areas. It was designed to be self-sufficient, recycling air, water, and nutrients. The structure was made of steel and glass, sealed to prevent air exchange with the outside world. It had its own atmosphere, maintained by the plants inside. The idea was to create a miniature Earth, a closed ecosystem that could support human life indefinitely. It was a test of whether we could build self-sufficient space habitats. The first mission began in 1991, with 8 people. They planned to stay for 2 years, growing their own food and recycling all resources. But problems developed quickly. Oxygen levels dropped from 21% to 14%, equivalent to being at an altitude of 13,000 feet. Carbon dioxide levels rose. The air became unhealthy. The scientists had to pump in oxygen from outside, breaking the closed system. Food production was difficult. Crops failed. Pests invaded. The scientists lost weight. They became hungry. They had to supplement their diet with stored food. The system wasn't producing enough. There were also conflicts. Living in close quarters for 2 years was stressful. People argued. Relationships strained. The psychological pressure was intense. A second mission in 1994 also had problems. The experiment taught us valuable lessons. Closed systems are hard. Very hard. Everything must work perfectly. One failure can cascade. One problem can become many problems. And that was on Earth, with help available if needed. In space there's no help. There's no backup. There's no way to fix problems if the system fails completely. But we've learned from Biosphere 2, modern life support systems are better. The International Space Station recycles about 93% of its water. It's working on recycling air more efficiently. Future systems might recycle 98 or 99% of resources. But even that might not be enough for million-year journeys. We'd need near-perfect recycling and systems that can repair themselves when they break. 8 people entered Biosphere 2 in 1991. They planned to stay for 2 years. They would grow their own food. They would recycle their air and water. They would live completely isolated from the outside world. But problems developed quickly. Oxygen levels dropped. Carbon dioxide levels rose. The air became unhealthy. The scientists had to pump in oxygen from outside. The experiment wasn't truly closed anymore. Food production was difficult. Crops failed. Pests invaded. The scientists lost weight. They became hungry. They had to supplement their diet with stored food. The system wasn't producing enough. There were also conflicts. Living in close quarters for 2 years was stressful. People argued. Relationships strained. The psychological pressure was intense. The experiment taught us valuable lessons. Closed systems are hard. Very hard. Everything must work perfectly. One failure can cascade. One problem can become many problems. And that was on Earth, with help available if needed. In space there's no help. There's no backup. There's no way to fix problems if the system fails completely. For an intergalactic journey, we'd need systems much more reliable than Biosphere 2. We'd need systems that can last for millions of years. We'd need systems that can repair themselves. We'd need systems that can adapt. It's an enormous challenge. But we're learning. We're getting better at life support. We're getting better at growing food. We're getting better at recycling. Maybe in the future, we'll be good enough. Maybe we'll be able to build self-sufficient spacecraft. Maybe we'll be able to sustain human life for thousands of years. There are also practical challenges. What if something breaks? We'd need spare parts. We'd need manufacturing capabilities. We'd need to be able to build new things from available materials. We'd need to be self-sufficient in every way. What if we encounter problems we didn't expect? What if there's an accident? What if there's a disease outbreak? What if there's a conflict? We'd need to handle these things ourselves. There's no one to call for help. We'd be on our own. But maybe these challenges aren't insurmountable. Maybe with better technology, with better understanding, we can solve them. Maybe we can build better life support systems. Maybe we can develop better medical care. Maybe we can create better psychological support. Maybe we can build spacecraft that are truly self-sufficient. The biological and practical challenges are real. They're significant. But humans are adaptable. We've survived in harsh environments before. We've learned to live in deserts, in Arctic regions, in space stations. Maybe we can learn to live in intergalactic spacecraft too. As you drift deeper into sleep, remember that humans are resilient. We've overcome challenges before. We've adapted, we've survived. Maybe we can do it again. Maybe we can become an intergalactic species. Maybe the challenges are just problems waiting to be solved. Chapter 9: Historical Context and Past Predictions. Before we explore realistic timelines, let's look at how predictions about space travel have evolved. History teaches us that technological progress is often unpredictable, and what seems impossible today might become routine tomorrow. In 1903, Konstantin Tsiolkovsky published Exploration of Cosmic Space by Means of Reaction Devices, laying the foundation for rocket science. At the time, powered flight was still a year away. Tsiolkovsky calculated that rockets could escape Earth's gravity, but he thought it would take centuries to develop the technology. It took 60 years. In 1926, Robert Goddard launched the first liquid-fueled rocket. It reached just 41 feet high. But Goddard envisioned rockets reaching the moon. He was ridiculed. The New York Times published an editorial mocking him, saying that rockets couldn't work in space because there's no air to push against. The Times later published a correction. In 1969, the day after Apollo 11 landed on the moon. In the 1950s, scientists thought nuclear-powered spacecraft might reach Mars by the 1980s. That didn't happen. But we did land on the moon in 1969, just 66 years after the Wright brothers' first flight. Progress was faster than many expected. In the 1970s, Gerard O'Neill proposed building space colonies using materials from the moon and asteroids. He thought we might have space colonies by the 1990s. That didn't happen either. But the International Space Station, completed in 2011, is a kind of space colony, just smaller and simpler than O'Neill envisioned. The lesson is that predictions are hard. Technology develops in unexpected ways. Breakthroughs happen when we least expect them, and what seems impossible often becomes possible faster than we think, or slower. There's no guarantee that intergalactic travel will happen, but history suggests we shouldn't rule it out. Chapter 10: Realistic Timelines. So when might intergalactic space travel become possible? When might we actually reach other galaxies? The answer depends on who you ask, and what you think is possible. Let's start with optimistic scenarios. If we make rapid breakthroughs in physics, if we discover new ways to generate energy, if we develop technologies we can't even imagine yet, maybe intergalactic travel could happen relatively soon. Maybe in a few hundred years. Maybe in 1,000 years. Some scientists think that if we can master fusion energy, if we can build better propulsion systems, if we can solve the biological challenges, we might be able to send generation ships to nearby galaxies within a few thousand years. The journey would still take millions of years, but we could start it. Others think that if we can develop wormholes or warp drives, if we can find ways to bend spacetime, intergalactic travel might become possible much sooner. Maybe in a few hundred years, maybe even sooner, but this requires breakthroughs we haven't made yet. It requires physics we don't understand yet. Realistic scenarios are more conservative. Based on current technology development rates, based on what we know is possible, intergalactic travel is probably centuries or millennia away. Maybe we'll develop better propulsion in the next 100 years. Maybe we'll master fusion in the next 200 years. Maybe we'll solve the biological challenges in the next few hundred years. But even with these developments, intergalactic travel would still be incredibly difficult. We'd still need to build enormous spacecraft. We'd still need to generate enormous amounts of energy. We'd still need to solve all the problems we've discussed. It's not going to happen quickly. Some experts think that intergalactic travel might not be possible for thousands of years, maybe 10,000 years, maybe more. The challenges are so great, the distances are so vast, that it might take that long to develop the necessary technology. Pessimistic scenarios suggest that intergalactic travel might never be possible. Maybe the physics barriers are insurmountable. Maybe we'll never be able to generate enough energy. Maybe we'll never be able to solve the biological challenges. Maybe intergalactic travel is fundamentally impossible. But even pessimists acknowledge that we don't know everything. We might discover new physics. We might develop new technologies. We might find solutions we haven't thought of yet. The future is uncertain. The Kardashev scale is a way to think about civilization development. Proposed by Russian astrophysicist Nikolai Kardashev in 1964, it measures how much energy a civilization can use. A Type 1 civilization can use all the energy available on its planet. A Type 2 civilization can use all the energy from its star. A Type 3 civilization can use all the energy from its galaxy. Currently, humanity is about a Type 0.7 civilization. We're not even Type 1 yet. To become a Type 1 civilization, we'd need to be able to control Earth's climate, harness all solar energy, maybe even control weather. We'd need to be able to use all the energy that reaches Earth from the Sun. That's about 174 petawatts, or 174,000 terawatts. Currently, we use about 18 terawatts, so we'd need to increase our energy use by about 10,000 times. The Kardashev scale was originally proposed with only 3 types, but scientists have extended it. A Type 0 civilization uses energy from organic sources: wood, coal, oil. That's where we were until recently. A Type 0.5 civilization uses energy from fossil fuels and early nuclear power. That's roughly where we are now. A Type 0.7 civilization is beginning to harness renewable energy on a large scale. We're transitioning from Type 0.7 toward Type 0.8, where renewable energy becomes dominant. Some scientists have proposed additional types. A Type 4 civilization would control energy on the scale of the observable universe. A Type 5 civilization would control energy from multiple universes. These are purely speculative, but they show how far civilization might develop. The transition between types isn't smooth. It requires major technological breakthroughs. Moving from Type 0 to Type 1 requires mastering renewable energy, climate control, and space-based power generation. Moving from Type 1 to Type 2 requires building Dyson spheres or similar megastructures. Moving from Type 2 to Type 3 requires expanding across the galaxy and harnessing energy from millions of stars. Each transition might take thousands of years, or it might happen faster if we make unexpected breakthroughs. The key is that intergalactic travel probably requires at least Type 2 technology, the ability to harness stellar energy. We're a long way from that, but the path is clear. We know what we need to do. The question is whether we can do it, and how long it will take. We're making progress. Solar energy is becoming cheaper. Wind energy is expanding. We're learning to harness renewable energy sources. But we're still far from Type 1. Some estimates suggest we might reach Type 1 in a few hundred years, if we continue developing. Others think it might take longer. Much longer. To become a Type 2 civilization, we'd need to harness all the energy from the Sun. That's about 3.8 times 10 to the 26th power watts. That's about 10 billion times more energy than Type 1. We'd need to build a Dyson sphere or something similar. We'd need to control stellar energy. We'd need technology far beyond what we have now. Some scientists think we might reach Type 2 in a few thousand years, if we continue developing. Others think it might take tens of thousands of years. Or hundreds of thousands. Or maybe we'll never reach it. We don't know. The future is uncertain. To become a Type 3 civilization, we'd need to harness energy from the entire galaxy. That's about 4 times 10 to the 37th power watts. That's about 10 billion times more energy than Type 2. We'd need to build Dyson spheres around millions of stars. We'd need to control galactic energy. We'd need technology that seems almost magical. If we could become a Type 3 civilization, intergalactic travel would be trivial. We'd have so much energy that traveling between galaxies would be easy. We could build enormous spacecraft. We could accelerate them to near-light speeds. We could send them anywhere. But we're a long way from Type 3. Very long. To become a Type 2 civilization, we'd need to build a Dyson sphere or something similar. We'd need to harness all the energy from the Sun. That's far beyond our current capabilities. But if we could do it, we'd have enough energy for intergalactic travel. To become a Type 3 civilization, we'd need to harness energy from the entire galaxy. That's almost unimaginable. But if we could do it, intergalactic travel would be trivial. We'd have so much energy that traveling between galaxies would be easy. So maybe the timeline depends on how quickly we develop as a civilization. If we become a Type 2 civilization in the next few thousand years, intergalactic travel might become possible. If it takes longer, it will take longer. If we never become Type 2, maybe intergalactic travel will never be possible. But there's another way to think about it. Maybe we don't need to become a Type 2 civilization to travel between galaxies. Maybe we just need better technology. Maybe we just need to solve specific problems. Maybe intergalactic travel is possible with less energy than we think. The truth is, we don't know. We can make educated guesses. We can extrapolate from current trends. We can think about what might be possible. But we don't know for sure. The future is uncertain. Technology develops in unexpected ways. Breakthroughs happen when we least expect them. Maybe intergalactic travel will happen in a few hundred years. Maybe it will take thousands of years. Maybe it will never happen. We don't know. But the question itself is interesting. The exploration is valuable. Even if we never travel between galaxies, thinking about it teaches us about physics, about technology, about ourselves. As you drift deeper into sleep, remember that timelines are uncertain, the future is unknown. But that's okay. The question is still worth asking. The exploration is still valuable. And maybe, just maybe, intergalactic travel will happen sooner than we think. Chapter 11. Alternative Perspectives. Maybe we're asking the wrong question. Maybe we don't need to travel between galaxies ourselves. Maybe there are other ways to explore, other ways to expand, other ways to become an intergalactic species. Let's think about probes. We could send robotic probes to other galaxies. They wouldn't need life support. They wouldn't need food or water. They wouldn't need to return. They'd just travel, explore, and send information back. That's much easier than sending people. We're already doing this within our solar system. We send probes to planets, we send rovers to Mars, we send orbiters to Jupiter and Saturn. We don't send people, we send machines. And it works. We learn a lot, we explore. we discover. The Voyager probes have taught us about the outer planets. The Cassini mission taught us about Saturn and its moons. The New Horizons mission taught us about Pluto. The Perseverance rover is teaching us about Mars. All without sending people. All with robotic explorers. For intergalactic exploration, we could do the same. We could send probes to Andromeda. They'd be small, they'd be cheap, they'd be fast. They wouldn't need life support. They wouldn't need to return. They'd just travel, explore, and send information back. But there's a problem. Even at the speed of light, information takes 2.5 million years to travel from Andromeda to Earth. So if a probe arrives at Andromeda and sends a signal back, we'd receive it 2.5 million years later. That's a long time to wait. By the time we receive the information, it might be outdated. The probe might have stopped working. The galaxy might have changed. Still, it might be worth it. We could send thousands of probes. We could send them to different galaxies. We could learn about the universe. We could explore without the risks and challenges of human travel. We could gather data that might help us understand if intergalactic travel is even worth attempting. For intergalactic travel, we could do the same thing. We could send probes to Andromeda. They'd take millions of years to arrive, but that's okay. We'd just wait. We'd send the probes and forget about them. Millions of years later, they'd arrive and start sending information back. But there's a problem. Even at the speed of light, information takes 2.5 million years to travel from Andromeda to Earth. So if a probe arrives at Andromeda and sends a signal back, we'd receive it 2.5 million years later. That's a long time to wait. Still, it might be worth it. We could send thousands of probes. We could send them to different galaxies. We could learn about the universe. We could explore without the risks and challenges of human travel. Artificial intelligence could make probes even more capable. AI could make decisions. AI could adapt to new situations. AI could explore autonomously. We wouldn't need to control them from Earth. They'd be independent explorers. Maybe we could send self-replicating probes. They'd arrive at a galaxy, explore it, build copies of themselves, and send the copies to other galaxies. Over millions of years, they could explore the entire universe. They could become an intergalactic network of explorers. Then there's the idea of digital existence. What if we could upload human minds into computers? What if we could send digital copies of ourselves to other galaxies? The journey would take millions of years, but the digital minds wouldn't care. They'd just be data, waiting. This raises questions. What is consciousness? Can it be digitized? Would a digital copy be the same person? These are deep questions. But if consciousness could be digitized, intergalactic travel would become much easier. We could send tiny probes with computer chips. We could send millions of them. They'd be cheap, they'd be fast, they wouldn't need life support. Virtual reality is another possibility. What if we could explore other galaxies without leaving Earth? What if we could build virtual simulations based on data from probes? We could experience other galaxies, we could explore them, we could learn about them, all without the risks and challenges of actual travel. Virtual reality technology is advancing rapidly. We can already create immersive experiences. We can simulate environments. We can create worlds that feel real. As technology improves, these simulations will become more realistic, more immersive, more convincing. Imagine putting on a VR headset and finding yourself in Andromeda. You could fly through the galaxy. You could visit stars. You could explore planets. You could experience what it might be like to actually be there, all based on real data from probes, all from the safety of Earth. This might be the most practical approach. Send probes to gather data, use that data to create virtual experiences, explore other galaxies from the safety of Earth. It's not the same as actually going, but it might be enough. It might satisfy our curiosity. It might fulfill our desire to explore. And virtual exploration has advantages. It's safe. It's fast. You can explore multiple galaxies in a single day. You can go back and revisit places. You can share experiences with others. You can explore without the enormous costs and risks of actual travel. But virtual exploration also has limitations. It's not real. You're not actually there. You're experiencing a simulation, a representation. It might feel real, but it's not. Some people might find that unsatisfying. They might want the real thing. They might want to actually go. Still, virtual reality might be a stepping stone. It might help us understand what we want to explore. It might help us decide if actual travel is worth it. It might prepare us for the real thing, if and when it becomes possible. Then there's the philosophical question. Why do we want to travel between galaxies? Is it for exploration? For survival? For expansion? For curiosity? Understanding our motivations might help us find better solutions. If it's for exploration, maybe probes are enough. If it's for survival, maybe we should focus on protecting Earth. If it's for expansion, maybe we should focus on our own galaxy first. If it's for curiosity, maybe virtual reality is enough. Maybe we don't need to travel between galaxies at all. Maybe our own galaxy is enough. The Milky Way contains hundreds of billions of stars. Each could have planets. Each could be explored. We have enough to explore right here. We don't need to go elsewhere. But maybe that's not the point. Maybe the point is the challenge itself. Maybe the point is pushing boundaries. Maybe the point is becoming something more than we are. Maybe intergalactic travel isn't about the destination. Maybe it's about the journey. About what we become along the way. As you drift deeper into sleep, remember that there are many ways to think about intergalactic travel, many perspectives, many possibilities. Maybe we'll travel between galaxies ourselves. Maybe we'll send probes. Maybe we'll explore virtually. Maybe we won't go at all. We don't know. But the question is worth asking. The exploration is valuable. And maybe, just maybe, we'll find a way. And now, as our extended journey through the cosmos comes to a close, let us return to where we began, the question of when intergalactic space travel might become possible. We've explored the scale of intergalactic space, the vast distances between galaxies, the millions of light-years that separate us from Andromeda. We've seen how current technology falls short, how our fastest spacecraft would take billions of years to reach even the nearest galaxy. We've examined the physics barriers, the speed of light as an absolute limit, the energy requirements that grow exponentially, the timescales that stretch into millions of years. We've seen how these barriers make intergalactic travel seem impossible. We've considered theoretical solutions: nuclear propulsion and antimatter engines, solar sails and ion drives, wormholes and warp drives, generation ships and cryogenic sleep, digital consciousness and self-replicating probes. Each solution has possibilities. Each has challenges. We've thought about the energy problem, the enormous amounts of energy needed, the difficulty of generating and storing it, the possibility of harnessing stellar energy, or mastering fusion. We've seen that energy is a barrier, but maybe not an insurmountable one. We've considered the biological challenges, the need for life support, the dangers of radiation, the problems of microgravity, the difficulty of sustaining human life for thousands of years. We've seen that these challenges are real, but may be solvable. We've explored realistic timelines, optimistic scenarios that suggest intergalactic travel might be possible in centuries, realistic scenarios that suggest millennia, pessimistic scenarios that suggest it might never happen. We've seen that the future is uncertain. We've thought about alternative perspectives. Maybe we don't need to travel ourselves. Maybe probes are enough. Maybe virtual reality is enough. maybe we don't need to go at all. We've seen that there are many ways to think about the question. The answer, ultimately, is that we don't know. We don't know when intergalactic space travel might become possible. We don't know if it will ever be possible. We don't know what technologies might emerge. We don't know what breakthroughs might happen. But the question itself is valuable. The exploration teaches us about physics, about technology, about ourselves, about our place in the universe. Even if we never travel between galaxies, thinking about it expands our understanding. It pushes our boundaries. It helps us grow. The universe is vast, almost incomprehensibly vast. Billions of galaxies, trillions of stars, endless possibilities. And we're here, on a small planet, asking big questions, wondering what might be possible, exploring what might be out there. Maybe intergalactic travel will happen. Maybe it won't. But the wonder remains. The curiosity remains. The desire to explore remains. And maybe that's enough. Maybe the question is more important than the answer. Maybe the journey of discovery is more valuable than the destination. So as you rest, let your mind drift with these possibilities. Imagine what might be. Imagine what could be. Imagine a future where humanity travels between galaxies, where we become an intergalactic species, where we explore the vast universe around us. The night sky is filled with galaxies, each one a possibility, each one a destination, each one a mystery waiting to be explored. And maybe, just maybe, someday we'll reach them. Maybe someday we'll travel between galaxies. Maybe someday we'll become something more than we are now. But even if we don't, the question remains. The wonder remains. The exploration continues. And that's something beautiful. That's something worth holding on to. Thank you for joining me on this extended exploration of intergalactic space travel. We've journeyed through vast distances, explored the limits of physics, considered theoretical solutions, and pondered the challenges ahead. If these calm, curious journeys help you unwind or spark your imagination, consider liking and subscribing to the channel. It helps others find their way here too. One sleepy soul at a time. The journey we've taken tonight is just the beginning. As we continue to explore, as we continue to learn, as we continue to wonder, new possibilities will emerge, new technologies will develop, new questions will arise. The universe is vast, the possibilities are endless, and the future, with all its uncertainties, is waiting. So rest well, and may your dreams drift among the galaxies. The question of intergalactic travel is vast and full of wonders, and the answer, whenever it comes, will be worth the wait. Good night, and may the stars guide your dreams.